it should be 20. This 5.1 milliseconds, let's see, this is 5.2 milliseconds, 5.1 milliseconds. So you have got one cycle and two cycles in 0.1 millisecond, which is 100 microseconds. So it is 20 kilometers.
According to
Yeah.
in point 1 you have to solve for 1 it is 0.05.
Right. Yeah, that's 20 kilometers. Okay, so let's see here. Now we can plot all at the same time. So if we click on this, we'll load up all the data. All right, this one here, we had a last plot. Let's see if I can. All right, so we can see here, this is IL1 plotted at run 1, which is the green one. IL1 plotted at run 2, which is 150 microseconds later. And then IL1 plotted at run 5, which is 750 microseconds. So you can see that first two have got this ringing effect, and then the current also is swinging. And it also has an effect on the transition, you can see here. Whereas the one which is totally avoids the ramp, running into the ramp effect, then your waveforms are pretty neat. The same thing is on the negative side. And here we can actually plot the diode current too. Let's go ahead and do that. Let's do a new window. And we're going to do. Let's see if we can plot. Let's plot the input current first for 750 microseconds. Right, so we'll do this. Okay, so I'm going to draw. This actually is a mistake. One second. Trace add IV in at 5. And we're going to minus it. IV in 1. Okay. This is the input current at 750 microsecond delay, and I'm going to just set it to 0. And let's do another plot. And let's say with this we do a plot ID1. Trace add ID1 anode. So I'm going to select currents, voltages, ID1 anode at 5. All right. So you have that current for D1, and now I'm going to zoom in to between 8 milliseconds, and we'll zoom into 10 milliseconds. And this is the top diode, right? Then we also plot the bottom diode.
Are they semiconductor models or just on resistance, off resistance, the diodes?
No, it is a semiconductor model. So you have a reverse recovery. We have tampered with some of the parameters which will cause convergence, but it is a semiconductor model. Yeah, it's like a semiconductor model. See the reverse recovery here, you can see right here the reverse recovery where you have negative current. And then we plot ID2, and we can see if things match up. Let's see, ID2. So trace, add, and I do to anode at 5. So, see, the D2 is coming, so in this particular period, you can see D2 is coming quite heavily on. So let me just zoom up further. Let me zoom up further here. So you can see that the top one is turning on pretty heavily, and then another reverse recovery. Now, here you could actually get a better diode, not a better diode model, actual diode model if you have bad reverse recovery. But normally if you're using a MOSFET, the diode, low voltage MOSFET doesn't have that bad of a recovery. So this is, but you can see the reverse recovery right here, and you can see D2 is coming on quite heavily during this phase. And then you have got D1 is playing minor part here. So this is the bottom diode, this is the top diode for phase A. And you can see the reflection here. This reverse recovery directly affects the input current. So one of the determination of power requirements. See, when you're using all PWM, this goes away significantly. So your ripple requirements go down because the reverse recovery of the diodes do cause stress on your capacitors. All right, so we're at 103. We have lunch downstairs, I believe, and we'll have an hour lunch break, and we'll then reconvene at 2 o'clock. And then we'll try to wrap it up by 5, and then start tomorrow again at 9.
Plus a component which is a switching frequency component plus voice switching frequency component.
Right.
So this component is creating this power. So if I split this current into the AC component and this current is equivalent to some component which is of switching frequency component and which is of the third harmonic component. This current is causing this power. This current is causing this power.
Right.
So this current is continuous current, whereas this current is not a continuous current.
Yeah. Correct.
So this power is a continuous power. This power is not a continuous power. If I see in the real time, on the time scale, this power is only the continuous power, whereas this power can be 0 for some time and can be negative, positive. All depends upon the switching frequency.
No, but it is the AC power.
There is a AC power.
Yes, so
but
that power will be continuous only. Now we are
the
having
magnitude
AC power.
the magnitude of the power is not constant always.
No, but that power will be the
No, but that can be
average.
This power is a peak power. So whatever you see over here is a peak power. So it's not a instantaneous power. So maybe if you see this power is a peak power, the total RMS power will be very small.
Can we do your total power factor?
We could. I think that's a good correct. We can actually do FFT on the voltage. Well, we can't because the voltage is the DC source, right? So
Yeah, that's right. Yeah,
DC source.
Yeah. FFT on the power and FFT on the current will be same in this case.
Well, we did the FFT on power, which said we have 49 watt at 20 kilohertz.
20
That means you have a voltage varying at 20 kilohertz and the current varying at 20 kilohertz, and they're in phase.
Yes.
They're exactly in phase. That's why you get 49 watts.
So this is also AC power only.
That's right. That's right.
But it's a power.
It's a power.
Yeah.
It's a power.
Yeah, that's
So
actually.
that is at that frequency. It's a power.
It's a power.
Yeah, but
I think
the
the-
frequency what we are using here is switching frequency equal. It's something like 20 kilohertz. So this power, it's not a continuously drawn power. Only the power which is DC power, it's a continuously drawn from the source.
That is also power.
See,
That is power.
it is power. I
Yeah.
think that the question is, see, the only thing we have is, we have a source, right? And when you have a source like a battery source, that 50 watt of power will not come from the battery because battery is incapable of supplying it, right? No battery is capable of supplying 20 kilohertz of power. So that power has to come from the capacitors.
No, all this is when the capacitor is not there.
Right, but we also have a perfect DC source. We have no,
No, but is it the case that the battery, the DC power which is coming from the battery, and if you have the capacitor, the power which is coming at 20 kilowatt, 20 kilohertz, that has to be replenished by the battery at whatever
a different rate.
different rate.
That's right,
But
that's
then
right.
the total power requirement or total power drawn from the battery could be the total of the two. You need power at 20 kilohertz, you need power at 40 kilohertz. You are putting a capacitor there to supply the power at that frequency.
That's an interesting point you raised. So okay, that's a very good point. Let's just think about that. Just a moment, one second. All right. So what you're saying is, now I think you raised a very important point. So let's see if we can understand this. Let's say we have got all right, so we have got, and we've got some impedance here. And you're saying that when we look at power here, this power is all, let's say, power at PF1 plus PF2 plus PF3. Okay, so on and so forth. This power here is P0, EDC, right? Now you're saying, okay, there has to be some components here, delta P, which is supplying those components, right? Yes. Right. Now, I think if you think about power, it is it's dW by dt, right? Power, or you can say energy, dE by dt. Okay, now this component already includes that replenishing. This 48 watt of component already includes that replenishing. Okay, so I can divide this 48 watt further into, there is some component which is purely, let's say P1 plus P2. Now normally P2 is much small because of this, because the replenishment is very slow. So if you because at the end of the day you want to balance the energy, right? The energy balance has to be there, right? So this component of 48 watt already includes the replenishment component for the capacitor. So you take out of that component and then you are supplying this power at that frequency.
there's nothing which says that the power components have to add up frequency wise. You just need the total balance of power. Instantaneous power as well as average power, they must balance the power.
Okay, lunchtime.
Torque on this thing, this example, or is it zero?
It's zero. It's really zero. Well, load torque is, you have got essentially, when we do the induction motor drives, then that's more of a variable speed model we have. This one is really fixed speed model, just to illustrate switching times and switching waveforms. But the load is you are actually injecting the current into the passive back EMF model. So you're still getting 48 watt of output power, so that's kind of load on the motor. Volts. Now here, the only change we have is that we have added 3 more AND gates, and we're still using one PWM channel, right? So if you're able to now, still we're using the same logic, high and low side logic. It's not on all the time. You have fixed duty cycles, time periods during which A top is on and B top is on, and so on and so forth. So all we have done is basically begin to PWM top and bottom switches during the logic decided by AT, BT, CT, A, B, B, C. Everything else remains the same. We just we added parameters, max duty, min duty, which is a parameter file, and we moved the amplifier which was here to a different sheet. So, but everything remains the same except that we added the PWM channels, and the logic remains the same. So we have a high side logic and the low side logic. So. The parameter file, it is pretty much the same, except we added these 2 parameters to the bottom. Maximum duty will be 195.05. Delay definition remains the same as before. And here is one simulation with the delay 1 of 0. The interesting part is this part is gone away, but you still have these linking. This part is gone away, but you still have this link. This is the input current. And now here, in this case, delay 1, 0, you have 80% efficiency, 47 input power, 38 output power. And if you match the delay exactly as required by the back EMF, then your efficiency goes up by 3 points and your output power also goes up slightly. About a watt or so, 1.5. Okay. Now here,
Efficiency calculations include the switching losses of the devices also, then the conduction losses.
this one includes everything. Everything. Yeah, it includes everything. So this one, see that is the part where when you do FFT of the output and the input, then it includes everything. Because here we are doing FFT on input power and output power. Now, So as we have increased the switching frequency, you can see that this is, yeah, that's a 20 kilohertz component. So these components have gone up. 20 kilohertz, 40 kilohertz. So your ripple capacitor requirements have gone up because of now you're switching high and low side. Here it looks like all the components are available, which would be something interesting to investigate. And here is the waveforms when you are perfectly matching the delay. They look pretty nice and steady. And this is just a brief comparison. Higher side you have got higher efficiency, high side PWM. High and low side PWM are lower efficiency. Input current harmonics less on high side, more on high and low side. I'm sure we can investigate a whole lot more. This is just to give you an example of how you can carry out your analysis. So let's do a quick demo. High and low side with variable delays. This will take a little bit of time. We'll close this. So here we have you can see, we'll turn off the grid. You can see better. So we have pretty much the same setup, except we have added 3 AND gates and coupled them with the PWM drive.